This PowerPoint presentation is entitled Dependent Samples T-Tests. The objectives are: the student will be able to describe when dependent samples t-tests should be conducted and carry out right-tailed, left-tailed, and two-tailed dependent samples t-tests. Dependent sample problems are appropriate for two scenarios. The first is when you have repeated measures on a single subject of students. The same single sample of individuals is measured more than once, such as when a pre-test post-test design is implemented. Consider a study in our class where we wanted to look at the effectiveness of instruction. I would give a pre-test to measure statistics knowledge before the class begins, then implement the treatment, which is the class, then give a post-test at the end. Because I have the same subjects that are measured at pre-test and post-test, that is called a repeated measures or a within subjects design. When we have two measures on the same people, we use a dependent samples t-tests to evaluate any differences. A second scenario where the dependent sample problem is appropriate is when you have matched pairs or matched subjects designs. Each subject in one sample is matched with the subject in the other. Matching is done so that the subjects are equivalent with respect to a variable that the researcher wants to control. Consider, for example, a weight loss study. When the researcher would like to know about the effectiveness of the weight loss, there are certain things such as starting weight that will play a role in the effectiveness of the treatment. What the researcher could do is match two males, for instance, with similar height and weight. He would put one of the males in one group, one in the other group. This matching process would be done for all participants. Because the participants are matched, there is some dependence on whether they were assigned to the first group or the second group. Whenever there is dependence in the data, from a pre-test to a post-test design, or through matching, the dependent samples t-test is appropriate. The null and alternative hypotheses for the dependent samples t-tests are H0 mu1 equals mu2 versus mu1 is mu1 minus mu2 equals 0, where the difference score is going to be computed, mu1 minus mu2. An alternative and more common way of writing the null and alternative hypothesis is to say H0 mu sub d equals 0, where mu sub d is the mean difference. Essentially, we are going to look at the difference between the pre-test scores and the post-test scores to determine if there is an effect. Again, as with every statistical test, you could have a two-sided test with a not equal sign in the alternative, a left-tailed test with a less than sign in the alternative, or a right-tailed test with a greater than sign in the alternative. It is important that the researcher decide which way the researcher will be taking the differences. The notation 1 and 2 denotes the group membership. The dependent samples t-test statistic looks very similar to the one sample t-test statistic. Essentially, it is a process of computing a one sample t-test on the different scores. The t with n-1 degrees of freedom, where n in this case is the number of subjects who have the paired data, so we still are looking at the number of subjects, is x bar d minus mu naught divided by sd over the square root of n. n-1 again are the degrees of freedom, and that will determine the row of the t-table that the critical value comes from. S sub d divided by the square root of n is also denoted s sub x bar d in some textbooks. This is an example of a dependent samples t-test problem. In a remedial math study, 10 students who scored more than 2 grade equivalents below their current grade participated in a remedial math program. The students were retested after 4 months in the program. Their initial and post-test scores are provided. Is there evidence that the remedial program was effective at the 0.05 level of significance? Well, in order to answer this question, you have to realize that there are 10 students and they were receiving two measures. The same 10 students received a pre-test and then a post-test. That makes this problem a dependent samples problem. The data are shown in this table. Student 1 had a 2.3 grade equivalent initially and a 3.4 on the post-test. The difference, taking post minus pre, is an increase of 1.1. Person 5 had an initial score of 2.4. The post-test score was 2.2. The post-test was actually lower than the pre-test, resulting in a difference of negative 0.2. The difference scores, post-test minus pre-test, were computed for every single individual. It is that difference data, the difference scores, that will be analyzed in the dependent samples t-test. The mean of those difference scores, if you add them up and divide by the number, is 0.42. The standard deviation is 0.4442. Again, we computed the difference scores and then computed the mean and standard deviation of the difference scores. To carry out the hypothesis test, we state the null and alternative hypothesis. The null, h naught mu sub d equals 0, versus the alternative, mu sub d is greater than 0. The research question asks whether there is evidence that the program is effective. In order to be effective, the post-test scores would have to be higher than the pre-test scores. The differences were taken post minus pre. If the difference is positive, that would indicate that the post-test scores were higher than the pre-test scores, which would mean that the program was effective. The appropriate test is the dependent samples t-test because, again, we have the same individuals that are measured at 2 time points. When you have the same group that is measured at 2 time points, the dependent samples test is appropriate. In computing the test statistic, the computation is x bar d minus mu naught divided by s sub d over the square root of n. Again, the mean x bar d is found by computing the difference scores and then finding the mean of those scores. S sub d is found by computing the difference scores and then the standard deviation of those scores. The test statistic is 2.99. To determine statistical significance, that test statistic is compared to the critical value. We are working with the t with 9 degrees of freedom, so we look at the t with 9 degrees of freedom row of the table. The alpha is 0.05. The critical value is 1.833, found by looking at the one-tailed alpha for 0.05 and the 9 degrees of freedom row of the table. We then compare our test statistic of 2.999 to our critical value of 1.833, and we conclude that we should reject the null hypothesis. There is evidence that the remedial math program was effective based on the data at the alpha equals 0.05 level of significance. Note that decision made based on p-values will be addressed when we evaluate SPSS output for the dependent samples case. We can also measure the effect size for the dependent samples case as we had for the one sample t-test case. The formula is very similar, x bar d minus mu naught divided by s sub d. Our guidelines for interpreting effect size remain the same. In this problem, our x bar d value was 0.42 divided by s sub d is 0.4442. This computationally turns out to be 0.95, indicating a large effect. The mean difference is just under 1 full standard deviation. Again, upon completing this PowerPoint presentation, you should be able to describe when dependent samples t-test should be conducted. There are 2 scenarios. One scenario is when you have a single sample receiving a pre-test and a post-test. We call that a repeated measures design, sometimes a paired samples design. The second scenario for carrying out a dependent samples t-test is when you have matched the data. That is, you are going to have two groups, but you determine group membership by finding two people with similar status and assigning them into each of the two groups. When you conduct a dependent samples t-test, it is very similar to a one-sample t-test. You essentially compute a one-sample t-test on the difference scores. You should be able to carry out right-tailed, left-tailed, and two-tailed dependent samples t-tests.